So in the last lecture, I ran out of time, so I didn't talk about this, but it's actually quite important for people, especially working on computational optimization. So when you are solving different types of optimization problems, right? For different problems, you might choose different types of solvers. Right? You may be wondering, which solver is the best, right? For a particular problem. So typically, people refer to this benchmark called Mittelman benchmark. The way it works is Professor Hans Mittelman, who is a professor at Arizona State University. Each year, before the Informs annual meeting, by the way, Informs is sort of the biggest conference in optimization in the United States. So before the Informs annual meeting, he will run some benchmarks on different types of optimization problems. And for years, it include commercial solvers like Cplex and Groovy and Express, but then at some point, some of these commercial solvers decided to withdraw from the benchmark. But it still can give you some insight, right? So here, as you can see, there are different types of problems. There are combinatorial optimization problems, linear programming problem. For example, if you want to say LP benchmark for finding optimal basic solution. Right? Then you can find the solvers being tested are listed here, right? And then it shows the number of problems solved and so forth for each solver. Okay. Then you could also check, for example, the MLP benchmark, because usually the MLP has more commercial value than other types of optimization problems. So as I said, Groovy, Cplex have already withdrawn from this benchmark, but you can still find some other solvers, like let's say COpt is a solver owned by a Chinese company. Skip is one of the best open source solver in mixed integer programs, and there are other solvers as well. So how do you look at this table here, right? As you can see, this table has 3 rows. The first 2 rows are related to the, I think, geometric mean of skewed and unskewed shifted geometric means of runtimes, right? So the smaller, the better it is, right? If you look at the skewed ones, that means one is the best, right? So COpt is the best in this list. And then the third row is the number of instances solved by each solver within this library. The library is called Mixed Integer Programming Library 2024. Okay. And then if you're interested in other problems, like you are curious which one is the best semi-definite programming solver, you can also refer to this benchmark. There are also benchmarks related to, let's say, nonlinear programs, mixed integer QCPs, mixed integer nonlinear programs, right? So this is a very nice website to keep track of. Okay. Any questions here? Okay. So now let me switch gears and then talk about the new lecture. We will talk about Langrangian dual and optimality conditions for general nonlinear programs. Right? As you follow the sequence of this class, we first talk about unconstrained programs. Then we talk about optimality conditions for linear programs. Then we talk about conic programs. Right? Then within continuous programs, the hardest thing you can think about is, let's say, general nonlinear continuous program. But then in this case, we mainly focus on convex problems. Okay, so we'll talk about how do you characterize the Langrangian dual for general nonlinear problems, and then what are the optimality conditions for convex nonlinear problems solution to be optimal. Okay. Again, let's revisit this slide. What do I mean by general nonlinear programs? You have a nonlinear function, objective function f of x. All the x are continuous variables, and then you have inequality constraints HL x and then equality constraint LJ of x. Right? Right? You can have multiple inequality and equality constraints. And then we use capital X to denote the feasible region of these nonlinear problems, right? Which include all the constraints in this problem. And then for some of the results we show in this lecture, it does not, the problem does not have to be convex. Some of the results will hold generally for nonlinear program, no matter the problem is convex or not. But some of the results we show in this lecture will only hold for convex problem, right? And then I will remind you which result hold for general problem, which result hold for convex problem only. So what does it mean for these nonlinear programs to be convex? Right? So in order for this nonlinear program to be convex, then all the inequality constraints must be convex. Right? So this describe if HILX is convex, then this describe a convex region. Right? This is like the sub-level sets of a convex function. And then the equality constraints must be linear in order for the feasible region to be convex. Right? You can imagine a nonlinear equality constraint. So for example, if I give you a nonlinear equality constraint in 2D, right? Draw any arbitrary line. Even if this line is a convex function, this line itself is not a convex set, right? This curve itself is not a convex set. You pick any two points on this curve, the line segment connecting these 2 points are not on this curve. Right? So that's why the equality constraint has to be linear. Okay. Any questions here?
Wait, I'm sorry. Can
Yeah.
you say that last part again?
Yeah. So for a convex problem, let's say constrained convex problem, right? The feasible region X has to be convex. Let's say the set X defined by these constraints have to be convex, right? In order for that to hold, the inequality constraints are convex, right? Right. And then the equality constraints must be linear. The reason is, let's say for this, just to give you a geometric view, if you have a nonlinear equality constraint, right? So let's say this constraint is y equals to x squared, right? So that means x and y has to lie on this curve, right? The curve is described by a nonlinear equation. So this curve itself is not a convex set, right? Although the function x squared is convex, right? If you pick any 2 points on this curve and draw a line segment, the line segment is not on this curve, right? The curve is describing this curve only. Yeah.
It's talking literally the only region that's viable is the curve.
Yeah, exactly. Yeah. So that's why intuitively the equality constraint has to be linear. Okay. Yeah. So now let's talk about optimality conditions. Right. Remember in unconstrained optimization problem, we have a first order optimality condition, right? What is that condition? If fx is convex, what is a first order optimality condition for x being optimal? Yeah, gradient equals to 0, right? If it is unconstrained, right? So here, as you can think about this theorem as a generalization of the first order condition for unconstrained problem. Okay. So here, the problem is constrained, right? Meaning that the feasible solution has to be in this set capital X. Okay. So suppose f is in a convex optimization problem and f is differentiable, then let x denote the feasible region. Then x star is an optimal solution if and only if this condition hold. Right? So x star is an optimal condition, then the gradient s star, the inner product of the gradient at x star with respect to any y, any feasible y, right? Minus x star has to be greater than or equal to 0. Okay, so how to interpret this condition, right? So you can think about this as at x star, any feasible direction will leads to an increase in the objective value, right? Because you can think about, let's say, you have a convex set here. This is a point x star, right? So that means if you pick any arbitrary point, let's say y, in the set, right? And then you want to move from x to y, right? So you are moving towards this direction that's denoted by y minus x star. Right? If you are moving from x star to y, this direction has a greater than or equal to product with the gradient of the objective at x star. Right? That means no matter which direction, which feasible direction you move within this this convex set, it will increase the function. Right? That means x star is the minimum. Okay, so that's sort of the intuitive way, not really the rigorous way of interpreting that, right? So now let's try to prove this first order optimality condition to see if we get any insight out of it, right? Okay, so now let's prove one direction. Let's say if this condition holds, then x star must be a global minimum for the convex optimization problem. Okay. Now, maybe let's say this is this direction. When the condition holds, the x star is the global minimum. Right? So how do we prove this? Any thoughts? Remember, there is some sort of a first order characterization of convex function that uses something similar to this, right? Right. So recall that the first order characterization of a convex function, right? So if f is convex, remember, so if you have a f of x that looks like this, right? If you pick any point here and then take the gradient at this point, it will underestimate the convex function, right? This is a so-called first order characterization of a convex function, right? So if f is convex, then we have fy greater than or equal to f of x plus the gradient at f of x, y minus x. Right, so this is called the first order characterization of a convex function. Right? The geometric interpretation is if you use the gradient to estimate the function here, this first order Taylor series expansion will underestimate the nonlinear function. Right? Hopefully, you still have some weak memory of that. Okay. So now. In this condition, the x and y can be chosen arbitrarily. Right? For any x and y, this condition holds as long as the function is convex. So now let's just choose x equals to x star. Right? So let's pick x equals to x star. Oh, sorry. Right. So now. If this condition holds, right, then we have, this term is greater than or equal to 0, right, when this condition holds. Now, if this is greater than or equal to 0, then we have fx star plus this inner product is greater than or equal to fx star, right? Okay. Now, since y can be chosen arbitrarily, right? And then when this condition hold, we have fy greater than or equal to fx star. Right? Now that means x star is the global minimum, right? So because y is chosen arbitrarily. Then you have x star is the right. Any questions here? Okay. Now let's show the other way. That is when fx star, when x star is the global minimum in this convex region, then this condition must hold. Okay. So how do we show that? So we can show that quickly by contradiction. Right? So let's assume there exists a y such that this condition doesn't hold. Right? So suppose there exists a y such that strictly less than 0. Okay. Now, so if we suppose this contradiction, we should be able to show that if this hold, x is not the global minimum. Right? So we need to find a point that is even smaller than fx star. So the way to do that is because you have a derivative, then you need to find some ways to generate a derivative in your proof. Right? So the way you can do it is playing the following trick. So let's consider intuitively if this is less than or equal to 0. And then that means intuitively if you move from x star to y, maybe there is a point that will decrease the function value. Right? So let's suppose you move from x star to y along the curve. So you can describe this green curve by x star plus t times y minus x, where t is from 0 to 1. Right. So if you draw this ray from x to y, right, essentially you are moving from x star to y. Right. So here, when you move from x star to y, this number t moves from 0 to 1. Right. Okay. So let's consider the function value on this curve here, right? Okay, so this basically describes the function value when you move from x star to y. Right? That's what this notation means here. Okay. So now let's think about what's the derivative with respect to t when t is 0. Right? So let's think about this as a function. So let's maybe denote this function as a function of t, because we already picked x star and y, right? They can be thought about as a constant. We are just moving t from 0 to 1, right? So let's treat that as a function of t. So what's a derivative of g over t at 0? Or yeah, it's nothing but, oh, sorry, this should be x star. it is nothing but this term here, right? Because you first take the, it's like following the chain rule, right? You first take the derivative with respect to x, then you take the derivative with respect to t, right? Then you get the gradient of fx star times the gradient with respect to t is y minus x star, right? So by assumption, you assume it's less than or equal to 0, right? So that means the derivative of g of t at 0 is less than 0, right? But now if you move from t from 0 to a slightly bigger number, g of t will decrease, right? Because its derivative is less than 0, right? So then that means in the neighborhood of x star, there is some value that is even smaller than fx star. Right? So think about the, if you have a function that is a scalar function, right? The derivative at this point is less than 0, right? And you follow the derivative direction. If you increase this value t, right, then this function value will decrease. Right? It's as simple as that. Okay. Yeah. Okay. So that's why this will hold a contradiction, meaning that x star is not even a local minimum. Okay. Yeah. So now, as you can see from this first order condition, it is not so easy to check how to check if the first order condition hold or not, because then you need to check for all the y in the feasible region, this condition has to hold. Right? It's not so easy to check, and it's not used in practice. Okay, so this is just the proof I wrote. Okay, so now I will try to derive the sort of easier to check condition. And then that condition is also derived using the Langrangian function. Okay. So hopefully this argument is easier to follow because we already covered Langrangian for linear programs. Okay. So now let's consider the Langrangian of these general nonlinear programs. Right? How does the Langrangian look like? It is nothing but f of x plus ui times hi, where u are greater than or equal to 0. Right? yu is greater than or equal to 0 here. Right? In the linear case, we did cover that. How do you choose the signs of the Langrangian multiplier? Right? Why do you want the u to be greater than or equal to 0 here?
Because we want to be Lagrangian lower bound, minimum.
Yeah, exactly. Yeah. So you want the Lagrangian to be a lower bound. And then for a feasible solution where hi of x is less than or equal to 0, right? And then you want u times hi to be less than or equal to 0 such that the Lagrangian is a lower bound. Right? And for the equality constraint, then you don't care. The v is unrestricted inside. Okay? So let's call it the Lagrangian here. And then it is not restricted to the convex case. Let's assume the Lagrangian is for any arbitrary function. Right? The results I'm going to cover in the next few slides will even hold for mixed integer programs. Okay, so now let's very quickly show why the Lagrangian dual function is a lower bound. Okay. So here the argument is for any u greater than or equal to 0, f of x is greater than or equal to x, u, and v. Right? now we have this particular lower bound inequality hold. Right? So let's go through this chain of inequalities step by step. So on the left-hand side, we have the optimal objective of the original problem. Let's denote them by fx star. Right? So this is the, let's say, optimal solution. X star is the optimal solution of the original problem. And then g of u and v is defined as the Langrangian dual function, which is basically after you dualize this constraint, then you minimize over x. Right? So this is defined as g of u of v is defined as minimization over x on this Langrangian here. Right? Just like we did in linear program, we use the Langrangian multiplier to relax the original problem, and then we take the minimum over x. Okay, so that's the two sides of the inequality. One is the optimal solution. The other side is the Langrangian dual function here. Okay, so let's show those inequality hold. So first of all, we are arguing the f of x star evaluated at optimal solution is greater than equal to this Langrangian at the optimal solution. Why is this true? Here. Yeah. So the reason is if you have x star to be the optimal solution, right? Then since x star is optimal, it must be feasible, right? So therefore, at x star, we have hi of x less than or equal to 0, and then lj of x equals to 0, right? And u is greater than or equal to 0 by construction. Therefore, all these terms should be less than or equal to 0 at the optimal solution. Okay, that's why this first inequality hold. Now the second inequality is saying it is greater than or equal to minimizing over x belonging to the feasible region over L of x uv. Why does the second inequality hold?
Because it's minimum.
Yeah.
Like the value of action can.
Yeah, exactly right. So this x star you pick is the optimal solution of the original problem. Right? X star is just one feasible solution, optimal for the original problem. But here we are taking the minimum over all the feasible solutions. Right? So that's why it has to be greater than. And then why does the third inequality hold? I'm just removing this constraint here. And then it is greater than or equal to this term. This hold trivially, right? Because you are just removing some of the constraint, right? You are making the feasible region bigger. That's why the third inequality hold. Okay. Yeah. So that shows you that by construction, if we pick any u greater than or equal to 0 and v, then this g of uv is always a lower bound, right? You can argue the other way. Because we need this argument to follow, that's why we need to pick u greater than or equal to 0 by construction. Okay. All right. So now I will show you a few examples of Langrangian dual for some nonlinear problems, right? Just to give some exercise, how do you get the Langrangian dual for some of the nonlinear functions, especially quadratic function, right? Remember, how did we get the dual for linear program is we take the dual and then try to maximize over the dual variables and so forth, right? Okay, so let's consider a problem that is slightly more complicated than linear programs, which is a quadratic program, x transpose qx plus c transpose x. And q is a positive definite, so it is a strongly convex quadratic problem. Okay, the constraints are all linear. Right? This is a standard form of a linear program. Okay. So how do we get the Lagrangian? Let's say we dualize all these constraints. So we pick u greater than equal to 0, and then it will be minus u transpose x, plus v transpose ax minus b. Right? So how do we get the optimal solution of this Lagrangian? Right? We are just minimizing over x. Right? What is the minimum of this function? Or how do you get the minimum with this function? I know that this is a strongly convex function. Right? What is a necessary sufficient condition to get the optimum of a strongly convex function?
Hessian should be positive.
Yeah, the Hessian is already positive definite, right? But then how do you get the minimum of a function like this? Right?
Well, you can set gradient.
Yeah, set the gradient to 0, right? Okay. So if you set the gradient to 0, what you will get is the gradient over x, lxu, we set equals to 0, and then this is nothing but q times x plus c minus u plus a transpose v equals to 0, right? And then here, q is a positive definite, right? So then this system of linear equations has a unique solution, right? Because q is full rank. Right? So q is full rank, then the optimal solution is essentially you take the inverse of that, then x is q inverse minus c plus u minus a transpose v, right? Yeah, it is just solving a system of linear equations. Okay. Now, what if q is not positive definite? Let's say if q is singular, what will happen? Right? So this part is one of my favorite part in this class. We will show you some results that will use linear algebra and also use shared complement, also use semi-definite programs. Right? So that's what we will show you in the next few slides. But I will gradually show you the result. Okay. So what if q is singular here, and then also q is positive semi-definite? How do you get the Lagrangian dual function? Here I'm just showing you the result. The result is quite nasty, but then we will show you step by step how do we derive that. Okay. Because when q is singular, you cannot just take the q inverse, right? This q inverse doesn't exist when q is singular. Okay. So before we try to derive the Lagrangian dual for a general quadratic program, let's review some linear algebra, right? Because we will need some linear algebra to derive that. Okay, I think I've shown this slide multiple times, right? What is the column space or the range space of a matrix A, right? The column space is all the linear combination of the columns of A, right? And then the row space is linear combination of row vectors of A. the null space is the set of vectors such that Ax equals to 0. Right? So then the row space is orthogonal to the null space, right? Because Ax equals to 0, that means each row will eliminate 1 degree of freedom for x. Okay. Yeah. So essentially, the problem of taking the Langrangian dual is like minimizing a quadratic function, where Q is not necessarily positive definite. Right? So if you look at this Langrangian term here, right? This is essentially minimizing a general quadratic function with some quadratic term, and there are some linear term with respect to x, right? And then a constant term. Right? So you can think about minimizing over a Langrangian function generally as minimizing of x over this quadratic term x transpose qx plus bx plus c. And then let's talk about the properties of this minimization problem with respect to the matrix Q and vector B. Right? So the first question we want to think about really quickly is, when is this problem unbounded? Right? If you solve a minimization problem over a quadratic function, when is it unbounded? Okay, unbounded meaning that the minimum is minus infinity here, right? Okay, now the easy to think about case is when Q is not positive semi-definite. Right? When a matrix is not positive semi-definite, that means there exists an eigenvector and a negative with a negative eigenvalue. Right? That's a definition of not being positive semi-definite. Right? Okay, so let's a negative eigenvector means QV equals to lambda V, where lambda is less than 0. Right? That's a definition for a negative eigenvector. Now let's set x equals to alpha times V, right? And then plug in. So what you will get by x transpose qx plus B transpose x plus c will be the following, right? Because x equals to lambda alpha v, and then qx equals to, so if you consider q of x, it will equal to alpha times lambda times v, right? So you can plug this in and get this quadratic function with respect to alpha. Okay, so you can do the calculation yourself. It should be very straightforward. You can for the sake of the argument, let's say if you believe me, you plug in the x, it will equal to this term. Right? So now it is a function of alpha, right? The v and lambda has been picked by me. I just pick a negative eigenvalue and corresponding eigenvector, right? Now, what is the sign of this term, right? Lambda is a negative, right? And then v transpose v, right? It's the norm of a vector. It must be positive, right? So therefore, the coefficient over alpha squared is negative. Now, this curve basically looks something like this, right? It is a quadratic function with respect to alpha, where the coefficient over alpha squared is negative, right? Now, if you let alpha equals to infinity, this problem will be unbounded, right? If you have a quadratic problem, the curve is facing downward, then it is unbounded whenever you set alpha equals to plus infinity or minus infinity. Right? So that already shows you when Q is not PSD, then this minimization problem is unbounded. Okay, just pick a sort of pick a negative eigenvalue and eigenvector that would do the job. Okay, so now if Q is positive semi-definite, what will happen? Okay, and there are also two cases we need to discuss. Right, the first case is if B is not in the column space of Q. Right, so the column space or the row, because Q here is a symmetric matrix, then the row space and the column space are the same here, right? So when B is not in the column space of Q, then that means there exists X such that Qy equals to, oh yeah, so this is too complicated. Let me explain step by step, right? So when Q is, when B is not in the column space of Q, that means B must have some of its part in the null space of Q, right? Because it's not entirely in the column space of Q. So therefore, you can find a vector Y, where Y is in the null space of Q, but B transpose Y is non-zero, right? Because B has some parts must be in the null space of a Q. Okay. Now, if you set X equals to alpha Y and let alpha goes to infinity, that will also give you an unbounded problem. Okay, how do you see that? Okay, so if X, because Y is in the null space of Q, then we have Q times X must be equals to 0, right? Therefore, this quadratic term, X transpose QX equals to 0, right? Now you are left with the linear term B transpose X is nothing but alpha times B transpose Y, right? Because B transpose Y can be non-zero, let's say it's negative, then you set alpha equals to plus infinity, this problem will be unbounded. Okay, that's the second case. You can try to digest that after the class. Okay. Now we are left with the third case where Q is positive semi-definite, and then B is in the range space of Q. Okay. So when Q is positive semi-definite, we know that the optimal solution is obtained at the gradient equals to 0. Right? So the gradient equals to 0 means Qx plus B equals to 0. Right? So when does Qx plus B equals to 0 has a solution? Yeah, so here, yeah, of course, when Q is non-singular, it has a solution. What about Q is singular? When does it have a solution?
When B is in a column space of Q.
Yeah, exactly right. So that means B is in the column space of Q, right? The linear combination of Q, the columns of Q can give you B, right? So that's pretty much what this condition is, right? So this linear equation has a solution if and only if B is in the column space of Q, right? So if this this equation doesn't have a solution, means that B is not totally in the column space of Q, right? B has some part in the null space of Q, right? That will fall into this case where you can show there exists a vector that will drive the problem to infinity, minus infinity, right? So that's sort of consistent with what we talked about before. Okay. Now, let's consider this case, right? We know that when B is in the column space of Q, it has a solution. But then, how do we describe this solution, right? Of course, let's say what happens to the solution of Qx equals to B, right? When Q is full rank, of course, you can just take the inverse of Q, right? But when Q is not inverse and then B is in the range of Q or the column space of Q, then you can express X as a pseudo-inverse of Q times B plus Z, where Q is a pseudo-inverse and Z is any vector in the null space of Q. Okay, you can check that is true. But then remember what is pseudo-inverse. We talk about pseudo-inverse in the last lecture, especially for PSD matrices, right? So when Q is symmetric, you can do eigenvalue decomposition like this, right? And the pseudo-inverse is defined by just take the reciprocal of the eigenvalues that are non-zero. Right? This is a pseudo-inverse of Q. So in order to get a solution, you can just use the pseudo-inverse times B. This will give you the characterization for the solution. Okay, so this is a little bit complicated. It involves some linear algebra you've learned before. Right? You can use this as an exercise of linear algebra. Right? That's why I kept repeating in this class. If you know linear algebra, you basically know optimization already. You probably will be able to derive many of the things here. Okay. Yeah. Now, let's go back why we have this particular term here, right? What if Q is singular, right? So remember, we basically talk about three instances. One is when Q is not PSD, this problem will be unbounded. And then when when B is not in the column space of Q, it will also be unbounded. The only case it is bounded is when Q is PSD, and then B is in the column space of Q. Right? That's the only case when it is bounded. So therefore, if you look at this problem, you can apply the results we just derived. Right? The only case when it is bounded is this linear term is in the column space of Q. Also, here we just assume Q is positive semi-definite. Therefore, you could use the pseudo-inverse here to get the minimum. Okay. Now, okay, what is more interesting is this general problem where we have a quadratic objective function here, right? And then M quadratic constraints, right? So this is a very general quadratic constraint, quadratic programs. Right? What is the Langrangian dual for this QCQP? So we will use the result we just derived to show you. Actually, it is a very shocking result. The Langrangian dual of the QCQP is a semi-definite programs. Okay, so we will show that quickly here. And here note that we do not assume any of the Q to be PSD. Right? So this is a general QCQP. This problem can be a non-convex problem when Q is not positive semi-definite. And then we want to derive the Langrangian dual for this problem. Okay. Now, in order to derive the Langrangian dual, you could multiply each of these constraints by lambda I greater than or equal to 0. Right? And then you arrive at this function parameterized by lambda. What are involved in the Q of lambda? It is Q0 plus lambda I times each of the Qi's in the constraints. And the linear terms are Q0 plus sort of like a linear combination, or actually Corny combination of all the Qi's, right? And the R's are here. Okay, so you can treat of this quadratic term as a function of lambda, and same wise the linear terms and the constant term as a function of lambda, right? Now this is a quadratic function, right? If you want to get the dual, then you will be minimizing over x, right? So this is something we've covered before. So g of lambda is minimizing this quadratic function over x, right? So what is this this minimization problem? First of all, when q lambda is not PSD, it will give you minus infinity. That's what we just discussed. And then when q lambda is PSD, but q is not in the column space of q lambda, then it is also unbounded, right? So therefore, using the result we shown you before, the only case when g lambda is bounded is when q lambda is in the range space of big Q lambda, and then this matrix q lambda is positive semi-definite, right? Then you arrive at this notation with a pseudo inverse. Okay. Yeah. So that's the Lagrangian dual function for a QCQP, right? Any questions so far? Or maybe you are already a little bit confused. Okay. Now, remember that after we derive this Lagrangian dual function, we show that this G lambda is a lower bound of the original problem, right? And remember, in the linear programming case, we will want to pick the dual variable such that this G lambda provide a bound that is as tight as possible, right? So the dual problem is maximization problem over lambda greater than equal to 0 G lambda, right? Okay. So how do we solve this problem, right? How do you solve the dual problem for the QCQP? It's not so straightforward because, how do you, of course, you don't care about the case where minus lambda, this G lambda function is unbounded, right? This case, if you give you a very trivial lower bound, what you care about is this case, right? And now the question is, how do you enforce this constraint such that you only let the lambda fall into this case, right? Because you want to find a lambda that give you a non-trivial lower bound. You don't care about this minus infinity case. You only care about this particular condition here. But then how do you enforce this condition in the dual, right? And then this is where the Scher's lemma comes into play. You can prove that this condition is equivalent to formulating the dual problem as a semi-definite programs. Okay, using the Scher's lemma. So let's show it very quickly, right? Now, this is a block matrix, right? This is 1D, and then this block is dimension n, right? So Q lambda is dimension n because Q is a square matrix. So according to the Scher's lemma, when this big matrix is positive semi-definite, it is equivalent to this lower diagonal block is positive semi-definite, and also R lambda minus D minus 1 over 2. This is basically what Scher's lemma said. This is greater than equal to 0 for all the Q lambda in the column space of Q. It should be Q lambda here, right? So now you sort of enforce a condition using the Scher's lemma, right? So here you have a Q lambda in the range space of big Q lambda, and it is PSD, okay? And then you can rearrange the inequality to show that this D has to satisfy this inequality, which is basically what you are trying to maximize. Okay, you can try to rederive this yourself, just looking at the notes and see how you derive this Lagrangian dual of the QCQP, and it is surprisingly equivalent to semi-definite programs. Right? So that's one of the reasons people care about semi-definite programs, because QCQP is a very general class of problem, right? If you can solve the dual of a general QCQP, you get a very tight bound for QCQPs, right? And this Lagrangian dual is also a convex problem. Okay. Yeah, so you wouldn't be able to, let's say, fully absorb if you just listen to me talking about that, right? So you should go back and then do the math yourself and see why this is true. Okay. Now, let's talk about some properties of the Lagrangian dual problem. We are you have this general problem, and then the Lagrangian dual problem is you try to find the maximum over the dual variable u and v, right? Where u is greater than or equal to 0. Right? The goal is to say, the GUV provides you with a lower bound. You want to find the tightest lower bound possible, right? Now, if let's assume the dual optimal value is G star, right? In linear program, we know that under some condition, strong duality hold and weak duality hold very easily, right? So the question is, does weak duality hold for general nonlinear problems, right? Even if the primal problem is non-convex, right? So we already showed that this always hold, right? Because remember we have a chain of inequality constraint. We argue for any u and v, it is a lower bound, right? Of course, if you take the maximum over u and v, it is still a lower bound, right? Because for the lower bound hold for any u and v. Okay. Yeah. So now let's show another property of the dual problem, right? So this is an interesting property to see that the dual problem is a convex optimization problem, even when the primal problem is not convex. Okay, it can be shown very easily here, right? So the idea is we want to check if this optimization problem is a convex problem. So we already showed for linear programs, right? The dual of the linear program is a linear program, of course. LP is convex. And we showed for any general QCQPs, its dual is an SDP, right? The SDP is a convex problem. Now, let's say if this property hold in general for any optimization problem, the Lagrangian dual problem written this way is a convex problem in U and V. Okay, so how do we show that? It can be shown very easily that this function g of uv is a convex function, because if you look at this particular minimization problem, of course it is equivalent to if you take a minus here and then multiply a minus inside. Okay. Now it is this function is taking the maximum over x, right? Now, this function is a linear function over u and v, right? So you can think about this term as having a large number of linear functions over u and v, right? So if you fix a given x, right? So let's say if x is fixed, then this term is a linear function over u and v, right? When x is fixed. Now let's suppose I have a bunch of x, right? I'm taking the maximum over x. It's like you are taking the maximum over a bunch of linear function of u and v, right? So what is the maximum over a bunch of linear functions? Right? So if you have, let's say you have 3 linear functions, the maximum over 3 linear functions is this curve here, right? Remember, the maximum over convex functions is convex, right? So that's what we covered in lecture 2. Right? So since the problem can be seen as a pointwise maximum over convex functions in u and v, in this case, it's actually linear functions in u and v, right? So therefore, it is this side is a convex function in u and v. And then the minus a convex function would be a concave function. Right? So you are taking the maximization over a concave function. That's why it is a concave maximization problem, and then that's a convex problem per se. Right? Okay, so that's a property to remember. Then we will come back to this property again when we show you the Lagrangian dual for mixed integer programs. Okay, so now we talk about strong duality. Then we've talked about this convexity property. the next thing we want to talk about is strong duality, right? When does strong duality hold for general convex nonlinear problems? So we won't have time to talk about all the cases where strong duality hold. There is a common condition people have used in the literature. It's called Slater's condition. Right? So under this Slater's condition, we will have strong duality. So the Slater's condition is saying if the primal is a convex problem, F is convex, all the H are convex, L's are linear functions, then there exists at least one strictly feasible solution. Right? Strictly feasible solution means there exists X where all the inequality constraints can hold strictly. Right? Under the Slater's condition, then strong duality holds. Okay, that's just a common condition people use in the literature. But to prove that, it will need a lot of work. So therefore, we'll just give you this condition. So then, at least when you read the literature, when you hear about Slater's condition, you don't get too nervous. That is just sort of like a strong duality condition, okay, for convex problem. Then with that, it is easy to calculate the duality gap, right? Because remember, one of the reasons we want to have the dual problem is to estimate how far the primal solution is from the dual solution. Right? And similarly, for nonlinear problem, you can do the same thing. In order to estimate how far your function value is from the optimum, because any feasible solution X is an upper bound of the original problem, the Langrangian dual function is always a lower bound. You can estimate the gap by taking the difference between a primal feasible solution and a dual feasible solution, right? Okay. So from an algorithmic point of view, we already said, right? If you ran simplex algorithm on the dual, then you can get an estimate on where you should stop, right? Similarly, in nonlinear problems, if you have a dual feasible solution, and then your tolerance is epsilon, all right? So if fx minus g, u, and v, primal minus dual is less than or equal to epsilon, then you can stop, all right? So that's one of the termination criteria you could use. Okay, so last but not least, we will talk about these famous Kharash-Quinn-Tucker conditions. The motivation of this condition is we want to have a easily computable condition to say for any general convex nonlinear problems, give you a necessary and sufficient condition for X to be optimal, right? So you can use this condition to design algorithm, right? Remember, in the all the algorithms are based on optimality condition, right? In the unconstrained case, we need to find a point where the gradient is 0. That's why you do gradient descent, right? And then in the linear programming case, the optimality condition is when you search all the basic feasible directions, they do not improve the objective, right? And then that's why you design the simplex algorithm that use the optimality condition, right? And then in nonlinear program, in order to design an algorithm, you also need an easy to check optimality condition, right? And then such that you can drive your solution to satisfy this optimality condition. We only give you a first order optimality condition, but that is very difficult to check. So you need a easy to check optimality condition in order to design an algorithm. That's where this Kharash-Quinn-Tucker condition come into play. So the reason it's called Kharash-Quinn-Tucker condition is because at some point people believe Quinn and Tucker were the first two guys to develop this condition. So I think they were both a PhD student and a faculty at Princeton, right? And then they discovered this condition. And then later on, people find out that someone else have already discovered that many years ago, right? So Kharash is a Russian mathematician. Actually, he discovered this condition for his master's thesis, right? So that gives you some sense what you can achieve for your master's thesis, right? So now it's a condition being used to solve, general convex or even general nonlinear programs, right? So I guess his master's thesis must be written in Russian, and then people find out later he was actually the first one to discover this optimality condition. Okay, so what does that include. Okay, so it includes 4 conditions, and it should be easy to interpret. Okay, the first condition, maybe let's start from primal feasibility and dual feasibility. Right? So if X and U, V are optimal, primal, and dual solutions, of course, they need to satisfy primal feasibility and dual feasibility. Right? In order to be optimal, the solution at least has to be feasible. Right? Then the first condition is relatively easy to interpret. It says the gradient with respect to x for this, this is like the Langrangian function. Right? The gradient must be equal to 0. That means the x you got must be minimizing the Langrangian function. Right? That's also sort of it because in order to to minimize the dual, then you need to take the gradient and set it to 0, right? Especially when this whole thing is convex. And then this condition, complementary slackness, is also what we have seen before, right? In linear programs. Remember when we said what is the necessary sufficient condition of a linear program, and it means primal feasibility, dual feasibility, and then you have complementary slackness, right? And similarly, in nonlinear program, this is a counterpart for that complementary slackness condition. Okay. Yeah. So then, because we want to show KKT condition is both necessary and sufficient under some conditions, right? So let's first show the necessity of the KKT condition. Right? So the theorem here is saying if X star and U and V star are primal and dual solutions with 0 duality gap, right? But not all the problems have 0 duality gap, but then at least we know under the latest condition, the problem will have 0 duality gap, right? But let's assume there is some condition holds, then you have 0 duality gap. Then we need to show that X star, U star, V star satisfy the KKT condition. Note that the necessity does not assume convexity, right? So that means as long as you have some conditions and then you show that the problem have 0 duality gap, then the KKT condition is necessary. Right? Of course, under the Slater's condition, the functions have to be convex. Right? There are other conditions where the problem will have 0 duality gap. Then as long as it has 0 duality gap, then the KKT condition has to hold. Okay, and the proof is just a few lines of inequalities, right? So because we know primal equals to dual, right? That's what we assume for a problem with strong duality. Then what is this G U star V star here? Because by definition, the G U star V star is obtained at the minimum of this Lagrange function. Just by definition, the Lagrangian dual function is the minimum of this function, right? So at the minimum, it must be less than equal to X star here, right? Because you are taking the minimum over X, it must be less than I pick the optimal X, right? Okay, so if I pick the optimal X, then that will be this equation here. Now this term is also less than equal to fx star. Okay. This is nothing but by construction, right? Because you have u to be greater than equal to 0. X star is a feasible solution, therefore this is less than equal to 0, right? Okay. So now with this bunch of argument, we have fx star less than equal to fx star here, right? So that means all these inequalities must hold strictly, right? Yeah. because you have f x star less than or equal to f, they are both f x star. Okay, so that means let's say, first of all, these terms must be, this whole thing must be 0, right? Right. So in order for this whole thing to be 0, each of these terms must be 0, right? Because it's less than or equal to 0, right? So then each of these terms must be 0, right? That's just complementarity condition, right? And then since x star minimizes this inequality also hold, right? Then the x star must be the minimum of this optimization problem, right? And since x star is the minimum, then the gradient at x star must be 0, right? That's for any optimum to hold. Okay, so therefore you got the complementarity condition and the stationarity condition. Okay, so you can check this argument here. Okay, and then I want to talk briefly about constraint qualifications, right? Note that I said under some conditions, the KKT condition will be a necessary condition. And one of these conditions is Slater's condition, right? But there are other constraint qualifications, right, under which the KKT condition will be necessary for a local or a global minimum. And then you can check the Wikipedia for the other constraint qualifications, right? So you can think about, again, constraint qualification as some conditions to hold, then KKT condition has to hold in order for a point to be optimal. And when you read the literature, you will probably see some of these constraint qualifications. Then the idea of showing this slide is not for you to understand each of these constraint qualifications. It's more about when you read about this in the literature, don't get too nervous. It's just under some conditions, then the KKT condition has to hold, okay? And then you can refer to the Wikipedia page if you see some of this in the literature. Okay, so now we will sort of prove the necessity of KKT conditions, right? And then we also need to prove sufficiency. Okay, so then for sufficiency, we need the KKT condition to be we need the problem to be convex, right? For a non-convex problem, even if you are at a KKT condition, you may not at a global minimum, right? You may at a local minimum, okay? So the sufficiency has to depend on the convexity of the problem, right? So when the problem is convex, if x star, u star, and v star satisfy the KKT conditions, then they are the primal and dual optimal solutions. Okay, so the proof is also quite simple. So you can assume if there exist these solutions that satisfy the KKT conditions, then by definition, since the problem is convex, right, and then as long as x star minimize the Langrangian function, then x star must be the minimum of must be equal to the minimum obtained at u star v star, right? And then this term must be equals to f x star, just because according to complementarity slackness, this term goes to 0. I mean, according to primal feasibility, this term goes to 0. Right? So that's why you have some primal and dual pairs which are equal to each other, and then they must be optimal, right? Because of weak duality, and then there is a 0 duality gap. Okay. The problem is okay. So that's sort of the same phrase of this condition. Okay. And then how do you apply KKT conditions to a convex problem? You could, for example, apply it to a quadratic problem with linear equality constraints. You can write down the KKT condition. Actually, for this particular problem, you could just solve a linear system to get the optimal solution. Right? This is just an exercise for you to show the KKT condition for that problem, and then I mean, for this simple problem, directly applying the KKT condition would be able to solve this problem. You don't need anything else, right? So in the next lecture, we will talk about what about for general nonlinear programs, how do you apply KKT condition and solve that problem, okay? Yeah, for the references, you could refer to some of the convex optimization notes and this very classic convex optimization textbook. The third bullet point is what I told you is one of my favorite parts in the Langrangian dual because it gives you some exercise on the concepts in linear algebra and then give you an exercise of semi-definite programming as well, right? But that part is usually not covered in the convex optimization book. If you are curious about Langrangian duality, you can check this last reference here. Okay.